Merci, nerd. لا تقول nerd. nerd. نهار أصاحبي. هدى. هدى.
ماشي اسمك.
هنا.
اسمك.
خويا زمزم. وي. قرجني معنا. You're into. No, midnight.
تبغي كل شيء
خصني البوط ديالهم.
Spaces, the structures that arise in the classical
relatively complicated expression depending on what you want. If you want to order, you just take some first derivatives and you'll get a tangent plane of every point. Euclidean space with one variables. And then the next thing we do is we start thinking about what structures on Euclidean space have the property that smooth functions are invariant under them. Okay, so the way you do that is you first think about functions with multiple outputs. So you take a function, I have Euclidean space on the source of high dimension and some other Euclidean space. I made it of the same dimension. I could have made different if I wanted. And that's now a function of multiple variables. So you say this is smooth if every component is smooth. So there's going to be a function f1 which is smooth, f2 which is smooth, and so on and so forth. Okay, and the first important notion of differential topology is the notion of diffeomorphism. Okay, so you now have a map from a space to itself. Okay, it's very easy to define what it means, for this map to be bijective, but you want to understand what it means for this map to really take smooth functions on the left to smooth functions on the right, and vice versa, for inverse to have the same property. So that has a name. It's called a diffeomorphism. And the way that I think about a diffeomorphism, the way to me most intuitive, is to think about polar coordinates. So the left-hand side is the usual, polar coordinates on the plane, the circles of given radius, the lines are sticking out in various directions. If I apply a diffeomorphism, the only thing that will happen, I'll now have new shapes on the right. But the key point is that the circles that I see on the left, when I transform them to the right, they don't intersect with each other. So that's the property that this map is. Not only that, I can also go back. You have to be careful because naively you would imagine that. Okay, x equals x cubed, we try to solve it. There's a unique solution if you work over the reals. But this map, and so it's a quantum but it's not a diffeomorphism because it's inverse at this cube root, and if you evaluate it 0, there's so hopefully not too many so far, but the next step is to define what it means to be a smooth manifold. So this is the problem with pure mathematics. There's so many layers built on top of each other. So what is a smooth manifold? So the most important thing to think about the smooth manifold is the topological space. blue one. It's a manifold on the left, the green one.
Can you take this mic?
I just think I'm not, the issue is that I'm not loud enough. Anyway, so the one on the right and the one on the left. What does it mean for them to be diffeomorphic? Okay. What it means for them to be diffeomorphic is that you can, again, bijectively map one to the other, fine, smoothly. What does smoothly mean? At first, you think I had to develop some new theory of what it means to be smooth. In reality, it's not very complicated, because remember at the very beginning, when I tried to tell you something, which at least I hope most of you know about what is it to have a smooth function on Euclidean space. The whole point is that smooth function on Euclidean space, the property being smooth is some property that is local. If a function is smooth at every point, then it is smooth. Okay, so you don't need to check the value at some point here and the value at some point over there, and then do some complicated computation to check whether the map is smooth or not. You just have to go to over here, you look at a small neighborhood, you say, can I find a polynomial that approximates this function to arbitrary order? Yes or no, okay? So now, let's say, I really need a big stick. Let's say that we have a map from this blue thing to this green thing, and it takes some point on this blue thing to some point on this green thing, okay? And I'm trying to define for you what it means for the map to be smooth. Okay. Otherwise, well, we're not doing topology with manifolds. We're just sticking to Euclidean spaces. So the first thing that I notice, or that I remember, is that this was a manifold. Okay. So locally near this point on the source, I have an identification with Euclidean space, which is canonical up to diffeomorphism. Okay. So because I know the notion of smoothness should be local, I can forget about everything else and just zoom in at that point. Okay? It's a small neighborhood which has this identification. Then I have this map. This point here goes over there, and similarly, that point over there has a neighborhood which is identified with Euclidean space. So by zooming in near that point and that point, I now can reduce the question of asking myself what it means for this map to be smooth to a question about Euclidean space where I already know the answer. Okay, so that means all I'm trying to suggest is that once you understand the local nature of smoothness, it's very easy to go from smoothness of maps from Euclidean spaces to smoothness of maps between manifolds. Okay, so now, are these two things diffeomorphic? Okay, now we go back to it. So, well, it would be good if I told you how I produced this left crinkled picture. And the way that I produce this left crinkled picture is that I first produced the right picture. I drew it by some parameterization, like literally drew 3 functions of 2 variables, which are periodic in the 2 variables, and then plotted this right-hand side. The way that I produced this picture is I took those 3 functions and I added some perturbations. I just added some higher order, powers of sine, sine of, and this has like sine x and cosine x, and this thing has like sine x plus 0.3 times sine of x, sine of 3x or something like that. Some more complicated expression. And now when you're trying to compare this to this, the first thing you may want to do is to see whether you can do the comparison locally. Okay? And that is the power of the bump functions that I explained earlier. So if I want to show that this blue thing is diffeomorphic to the green thing, it turned out in practice, it's what you can do is you can go from patch to patch and just make some identification from one patch to the other, deform the green thing to the green thing, to the blue thing to the green thing one step at a time until you can then glue them all together and attain the desired diffeomorphism. And this is again, extremely important feature of differential topology, which is that the only invariant of smooth manifolds are discrete invariants. Okay? There's no so that's called flexibility in some sense. There's no continuous in k-parameter families. Okay? There's no one parameter family of tori. From the point of view of differential topology, there's only one. Once you fix this one, the other ones are all diffeomorphic to it. In order to get something non-diffeomorphic, I have to do something very radical. I have to take 2 of these and glue them together and do some much more complicated construction. Now, just to not misguide anybody, once you have this notion of smooth manifolds, it's very easy to then build on top of this some notions in which you can restore rigidity. What I mean by rigidity is something like, if I drew a triangle in the plane, okay, like we're doing now, back to doing Euclidean geometry, Okay, like in, well, anyway, middle school. I don't know exactly when people learn this anymore. Yeah, so you draw a triangle in the plane, and you take some point in the triangle and you move it a little bit, and you ask yourself, are these triangles congruent? And the answer is generally no. The triangles are going to be very different. You're not going to be able to map from one to the other by a orthogonal transformation. Okay. In differential topology, that's not what you see. But you can restore this rigidity by going back to geometry and having some notion of distance. So this blue thing lives in 3 space. I take any 2 points. There's a distance between them. You don't want to take the straight line distance. It's better to take the distance along the manifold. It's not a big deal. This green thing will also have a notion of distance between 2 points. And it's, again, not very difficult to prove that as soon as you do any reasonable deformation of the blue thing, you will get something which notion of distance is very different. Okay, so Riemannian geometry or metric geometry, unlike topology, is very rigid. Okay, so that's not what we're going to do. Flexible, like differential topology. You very hard to deform things in such a way that you get things which are inequivalent. But then, surprisingly, about 40 years ago, it was understood that it has some hidden rigidity in it. Okay? And that's somehow the fundamental dichotomy in the subject. Any questions before I move on? Because I'm about to, kind of switch gears to start talking about symplectic things. أنا عرفت شنو؟ أنا بوصلك.
No. What do you mean by rigidity?
Okay, so rigidity here means intuitively that if you take a construction and you change it a little bit, the result is different from what you started with. Okay, so if you perturb, things are now become inequivalent. Flexibility is the opposite. You do a construction, you change a few parameters around, it's still the same thing. Okay, and it's some kind of, there's mathematics, pure mathematics has a lot of this. Different areas lie on different parts of this divide. Parts where you have to be very careful, estimate things carefully, whether you get your correct epsilon or multiply the epsilon by 2, it makes a huge difference. And parts where you can set epsilon to be 2 million. It doesn't matter. That's not the question we're asking. Does that make sense?
I have a question. I just don't understand what you mean by invariant, and why is it that they are discrete? I still don't get this.
So I think there will be an example in a second, but let me just give you a very basic example of an invariant. So if I have a triangle in the plane, okay, and I ask myself, are these two triangles similar? Is there an orthogonal transformation that takes one to the other? There are invariants, which are the angles at the vertices. Okay, that is a continuous invariant. Okay, so a discrete invariant that I have in mind is like something like I have a polygon. It has n sides. Okay? In order to switch from n to n plus 1, that is a rather violent process. I had to take an edge and I had to break it. Okay? But so that's this rigid mathematics tends to have continuous invariants like angles or like the perimeter or the area or something like that, and flexible mathematics tends to only have things which are discrete. Okay? And in fact, what I'm trying to say is symplectic topology is somehow in between.
What is the mathematical definition?
There's no mathematical. I mean, one could try to give a mathematical definition, but I'm not. Not exactly what I'm trying to aim for. Okay, any more questions? Lord.
Sure, Professor. Thank you for this presentation. But thank you for this presentation and for this conference. And my question is of I have a topological space, is hard to local is hard to define the diffeomorphism locally. Is hard. Is need to this manifold in Euclidean space.
So the
locality is not a clear definition of locality, because if you have abstract topological space, is hard to define the diffeomorphism for this local space on vector space or Euclidean space.
Yeah, so a general topological space will not be a manifold. Okay, but what you can do is you can say, if I have a topological space, then there's some condition. Maybe it has to be Hausdorff and second countable, which I don't want to talk about what that means. Okay, then there'll be a notion of open set, and that's what a topology is. And then this locality condition is something like, at every point, okay, there is a basis of open sets, okay, which have these identifications with Euclidean space, and then you can get them. But the key idea is to have the notion of a basis of open sets near every point, and that's what allows you to formulate locality in this setting. Yeah, one more question.
Please, I cannot understand why the manifold has only 2 dimensions.
This one.
Yeah, why?
Okay, so what does this picture mean? Sorry. So this picture lives in space. Okay. So this is so there is some solid shape in there that you see, and what we're doing is we're taking only the boundary of it. Okay, only the outside. So for example, if we had this globe which isn't here, of the planet Earth, we're taking only the outside of it, not the part inside. Okay? And if we know, so the Earth that we live on is a sphere, is a 2-sphere, and at every point we can identify this 2-sphere with Euclidean space. That's what maps are. If we have a map of a country, what we have is we have a local presentation of this manifold that we live in. It's a complicated, well, it is the simplest compact manifold, but it's okay. A manifold we live in as we identify it with the Euclidean space. So this object that I drew here is similarly, I'm not taking the inside, I'm only taking the boundary of it, the part that's, well, I don't quite know how to say more than that.
It has only 2 dimensions.
It has only 2 dimensions because I don't take the points that are, I only take the points that I can see. Does that make sense? Okay. Yeah. Okay. So من أعطيت محاضرة عادة بالإنجليزية يقولوا دونات. Okay. ولكن إحنا نقول شفنج. تأخذ شفنج تعمل شفنج في الزيت. Okay. الموضع اللي تتلقى فيه شفنج مع الزيت داك الشيء تهضروا عليه. Okay. So now, unfortunately, we have to switch to something harder. So my goal is to define something called symplectic manifold. Okay. But to define this thing called symplectic manifold, I need more mathematics. Okay. I need the notion of differential forms. Okay. So differential forms were basically invented by theorem. Theorem was trying to, well, it's a little bit hard. He was constructing invariants of manifold. But the way that you should think about differential forms, if you have not seen them, as I imagine most of you have not seen them, is that you should think of them as some way of formalizing the notion of integration. Differential forms are made to integrate, to be integrated. So every differential form, I'm not going to define it. Okay, a differential form has a number associated to it. I'm going to call it K. So for example, I'm going to focus on 2 forms. Okay? So 2 forms are made to be integrated on surfaces. That is what that is how they have been defined. They have defined for this purpose. So if I have a differential form on Euclidean space in n variables, my Euclidean space in n variables is going to have some kind of coordinates, x1 through xn. Okay, people can, okay, maybe I can stand here for a second and hope not to disrupt the thing. So the x1 through xn, and the definition of a differential form is some expression of this nature, a collection of smooth functions, they're called here omega ij, okay, that are labeled by pairs I and j of variables. Okay, so and then there is this symbol wedge in between. Just ignore it for now. As I said, the most important thing, the thing that differential forms were designed for, is to be integrated. Now, you cannot integrate something two-dimensional on something n-dimensional. Okay, so what you do instead is you take a two-dimensional object mapping to your n-dimensional thing. So that's this map U. I take a differential form in n variables. Okay, that's called omega. It has the I take a map U from R2 to S to Rn. Okay, so R2 is going to have some coordinates as well, and I'm going to call them S and T. So that's this S and T. And then there is this, if you have a function of Rn, you can just compose it with the map U. So then you will write something like omega I of U. Okay, or in this case, omega ij of U, because my function has these two. I have a bunch of functions labeled by two variables. And what we do here is we say, okay, now that we have a map from R2 to Rn, we can. The terminology is pullback, but let's just ignore it. We can integrate this two form along this surface, the surface formed by the image of this plane. And this integration is defined in the kind of, well, again, ultimately in the only way that makes integration make sense, which is you add up over all the variables I and j, a bunch of integrals. That's what's happening in here. There's a sum, this sum, big sum over here. Symbol over here is sum over the pairs I and j. And what you do, well, okay, if I had a single function, okay, I can just integrate a single function over ds and dt. Okay? But you have to be careful. You don't integrate the function of ds dt. You integrate with this determinant of the Jacobian matrix. So again, if somebody here has seen any kind of integration in first of all, if you have seen any kind of integration in one variable, you have seen this, because there is a change. What is it called? I always forget what it's called. I'm sorry, I only know the names in English. Well, no, the chain rule, the opposite of the chain rule. Anyway, U substitution. That's what it's called. We call it U substitution. So you're trying to integrate a function, and then you compose it with another function. You like to know what is the integral of that, and you see a derivative appearing, which is what's happening in this determinant part. If you have multiple variables, instead of a single derivative, you have to take the derivative. You have to take the determinant of the matrix formed by all the first derivatives. That's what I wrote over there. Okay, so that's what a differential form is. And the one thing that I want you to have in mind is that there is this determinant that appears over there. Okay, it's determinant of the first derivatives. Ooh, I'm sorry. Well, I should have written partial s u ui rather than partial s xi. Both notations are acceptable. But anyway, this determinant has a geometric meaning. Okay, and the geometric meaning is that over here I drew a plane, two-dimensional plane. This axis is xi. This axis is xj, basically. And when I take the derivative with partial s and partial t, I get two vectors. Okay, and that determinant is the area of this parallelogram. Okay? And that's the sense, or at least one of the senses in which you should think of integration of two variables as having to do with area, just like integration in one variable has to do with length. Okay, so anyway, so that's the definition. Let me move to the next slide. No, I'm not sure this is. Maybe actually I'll stop here. Is this okay? No. Okay, I don't know what to say. This is differential forms are very hard, so I think there's not much more I can say than this. But let me say the next thing, because the next thing, now we can have some real questions. So there's two very important notions for differential forms. So the first one is the notion of being closed. Okay, so if anybody in here has taken a course involving complex analysis, you will know something called the Cauchy formula, Cauchy residue formula. Cauchy residue formula is always very puzzling. You do some integral, and you always end up with an integer. Okay? That's basically what it's about. So from the point of view of a topologist, and of course what really happened here is that this kind of mathematics was discovered in the 19th century in the setting of complex variables. Poincaré knew about it, and then it was developed so kind of in a more formal setting. And the formal setting is the notion of a closed differential form. So a closed differential form has the property that if you try to integrate it along a manifold and you deform the manifold, the answer doesn't change. So let me give you an example. So in polar coordinates, we can write on the plane, theta variable that goes around once, and r variable, which is the radial direction. And I'm going to consider a one form in this case, not a two form. The one form I'm going to write is d theta. And I'm interested in integrating d theta. Now, anybody who knows anything about integration in one variable can integrate d theta on this circle on the left. It is very easy because all that's going to happen is that this circle is itself parameterized from theta going from 0 to 2 pi. Okay, and you integrate d theta and you get 2 pi. It's very easy. You're integrating one. Now, let's look on this thing on the right. Okay? How would you possibly integrate d? I mean, I didn't give you an equation, but you can just imagine. You write something very complicated. How would you possibly integrate, d theta on a complicated curve? So a priori, you would guess, well, the answer might be some very complicated thing and might change depending on the number of, if you deform it a little bit. And the answer is no. D theta is a closed differential form. Okay, it doesn't matter what shape you pick on the right, as long as it goes around the origin. The origin is the central point, 0, 0. As long as it goes around the origin one time, okay, the integral will be 2 pi. So the integral on the right is also 2 pi. Okay, so again, just small comment. So this is much of what pure mathematics is. You start with this computation in the 19th century, okay, with this observation in the 19th century. To be honest, what happens in Cauchy integral formula is not exactly this. You could rephrase it like this. You start with this observation, and then you try to think about why is it true. Okay, so you formulate a whole mathematical theory about why it is true, and that is what the previous slide is about, even though it just hints that it exists. That's what differential forms are about. That's what theorem did. Okay? And the advantage is once you've done that, you can then work in higher dimensions, and you don't have to rely on our intuition and on being able to draw these basic pictures. Okay, so this is the notion of being closed. And then the other notion that I need is the notion of being non-degenerate. Okay, so remember. So we'll talk just about two forms. So two forms are things that are made to be integrated on surfaces. Huh? So it's very easy. 0. Okay. You can imagine that you have some recipe that you integrated on any surface, you could get 0. That is the most degenerate example you can pick. So what is the correct notion of being non-degenerate? It should be something which is maximally non-zero. Okay? So if you look in the textbooks, you will get some definition. Okay, and definition is of course the correct definition, but the way to think about it is as follows. So a two form is non-degenerate if the following happened. Every time I pick one direction, okay, I have this direction here, I can choose another direction so that the plane which they span has the property that if I integrate omega over it, I get a non-zero number. Okay, so you cannot formulate the non-degeneracy just in terms of one direction alone. It's a statement that says if you pick a direction, you can always complement it so that the integral is non-zero. If you did something more naive, like, for example, you said the integral on any two plane is non-zero, it's very easy to show that that doesn't make sense. And you will never find something that satisfies this property, and this turns out to be the correct one. Okay, oh yes, and then, maybe you didn't understand what I said, but it's a linear algebra exercise, which it would be good maybe for somebody to try to see whether they understand. They can reconstruct anything what I said to show that if you make this assumption, then in fact the dimension is even. And of course, statements like this, the way you should think about it is, I'm asserting that there is no example of a non-degenerate two form in one variable, in R1. That's actually very easy because of this. You need a dx1 and a dx2. That's fine. But the real thing that I'm saying is that there is none in 3 dimensions. If you pick something in 3 dimensions, there will always be one direction along which, if you try to perform this procedure, you will always get 0. Okay? You take this one direction, you pair it with anything else, you'll always get 0. So that's linear algebra exercise. Okay, questions before I move on? Okay, next slide is going to say what a symplectic manifold is. So, okay, I will move on. Good. So what is a symplectic manifold? So that's the subject. That's what I study in some sense. So a symplectic manifold has a smooth manifold with a non-degenerate 2 form. Okay, closed and non-degenerate 2 form. So what it means in particular is it's something that has a notion of area. Okay, you can integrate it. You can integrate the 2 form on surfaces, and the simplest setting would be if you just assume that the manifold is dimension 2. Okay? So if you have a manifold of dimension 2 and it has an area form, you have a notion of being able to figure out how big things are in terms of the volume, but really 2-dimensional volume, then you have a symplectic manifold. And so this picture on the right is a symplectic manifold. So how am I thinking of area? I'm thinking of area like this. I have my surface, and I'm asking myself, I would like to paint it in blue. How much paint did I use? Okay, that's the area that this manifold has. The green thing was painted in blue. In green, I used some amount of paint as well that has its area. Now, the first first result in symplectic topology says that, in fact, for surfaces, this is a complete invariant. Okay? So what I mean, as long as the number of holes is the same. So if I take the blue thing and I take the green thing, and if I needed the same amount of paint to paint the blue thing as I needed to paint the green thing, or a different color, then not only are these two things diffeomorphic, like I was trying to explain earlier, because one of them is just obtained by deforming the other, and we have bump functions in differential topology. It's very easy to follow these deformations by diffeomorphisms. Not only are they diffeomorphic, but I can choose the diffeomorphism in such a way that it preserves area pointwise. Okay, that at every point I don't stretch, or rather, if I stretch in this direction, then I must be shrinking in another direction so that the total amount of area doesn't change. So that's the first result in symplectic topology. And now there's some kind of point here where, again, we have to go back to this notion of symplectibility, rigidity and flexibility. And what's going to happen is I'm going to say something like this. There's this one invariant, which is the area, okay? And it is a continuous invariant. But what I'm going to do is I'm going to always imagine that it's fixed. Okay? And the question is, once you fix this, what's left? What are interesting invariants of symplectic manifolds, and how can I understand them? Okay, so let me, actually, this is a good place I'm going to explain the slide, and I'm going to pause for a second. So the first hint that there is something interesting happening in symplectic topology occurred at around 1915. So Poincaré proved, actually what he did is he announced and then never proved the theorem. I think he died in the meantime. A theorem which is now called the Poincaré's last geometric theorem. So I would like to explain what this theorem says. Okay. So, we have this notion of a symplectic manifold. It makes sense in arbitrary dimensions, but we're only going to think about it in this dimension. And the symplectic manifold that I'm interested in is this annulus. Okay, so I take a region in the plane, I take a circle, the red circle, and I take the blue circle. So I take the disk that it bounds. It's this yellow region, and I remove the blue circle, the inside of the blue circle from it. So this is an annulus. And Poincaré was interested in this in the annulus because it arises as something called the surface of section in some 3-dimensional dynamics problem, which is related to celestial mechanics. But let me just state the question he asked. So assume that you have a transformation of this annulus and maps it back to itself that preserves area at every point. I'm going to call this a symplectic transformation in this lecture. And assume that on the red circle, it rotates a little bit in one direction. So I pointed it, I guess this is counterclockwise. And on the blue circle, it rotates in the other direction. So the question that he wanted to ask is, must there be a point that is fixed? So a fixed point is a point that under this map is taken to itself. Okay? And the theorem, which again Birkhoff really proved, is that in fact there must be two and we come to do with multiplicity. Okay? And they're shown over here. So this result is very surprising because the area preserving condition is essential. So I drew over here the graph of a function from R to R, so from maybe -1 to -1. The function is in red, and it's pretty clear that this function has a smooth inverse. And in blue is the identity map. Okay? So the fact that this red line and this blue line only meet at the endpoints, so that tells you that the corresponding diffeomorphism of the interval has no fixed points, except at 0 and 1. So what you can do is you can take, in the radial direction, you can take this function. Maybe it's a bit better to do it from 1 to 2, but anyway, in the radial direction, you can this function, and then in the rotational direction, in the angular direction, what you can do is you can do any rotation you want, but follow Poincaré and make the rotation be non-trivial on one side and non-trivial on the other side, let's say in opposite ways. Now, if you look at the combined transformation, what you see is that there's no fixed point. And why is that? Well, the map that I picked, if I look at it, any point where the derivative of this red function is not equal to 1, any point is not, that will be a point where the map is not area preserving. Okay? So this is something, this contradicts the conclusion of Poincaré's theorem when you drop the assumption that the map is area preserving. Okay. So any question about this? So it's supposed to be something that you could actually think about and visualize what an area preserving transformation of the annulus would look like, but maybe I will pause before continuing further. Okay, I will continue. So now, you can now, once you have this result, you can ask yourself, can I generalize it to other surfaces? But one thing you could try to do is generalize it to higher dimensions. Okay, so this is where Arnold comes in. So the naive generalization is to say, well, I have this notion of area, maybe I should look at volume. That doesn't work. Okay? You do the same thing, you take the analog of the annulus, which is like you take a ball and you remove a ball from it, and you will not be able to prove a result of this of the nature of Poincaré's result. Okay, so in the 1960s, Vladimir Arnold realized that the correct generalization takes place in the setting of symplectic manifolds. Okay, so the statement of the conjecture is a little bit technical because there's this word simply connected in it. Please ignore it. Okay, it says if you take a diffeomorphism of a compact symplectic manifold, that the compactness so that I don't have to say something at the boundary, which preserves the symplectic form, then it must have at least 2 fixed points. Okay, technically there's at least 2 with multiplicity. The actual statement of Arnold's conjecture involves homology theory. I will say something about it in the end. Okay, so this conjecture that there must be at least 2 fixed points is actually motivated by a basic result in differential topology. So I'm going to remind you, if you have a smooth function, you say that you have a critical point if all the first derivatives vanish. That's what I wrote over here. Okay? And now, I'm not going to give exercises for the audience. I'm not going to put you on the spot, but we should all be able to prove that if you take a smooth function on a compact manifold, then there must be at least 2 critical points. Okay? So the reason, I'm saying we should all be able to prove, there's one step. It's really combining 2 ideas. One idea only uses topology and the notion of continuity. And that simply says, if you take a compact manifold and you look at every smooth function is continuous. If you take a continuous function on it, then it must have a min and it must have a max. Okay, that's the first thing. This is just some statement about continuous functions. The next thing is, if it has a min and a max, now you need to do some small amount of analysis, and analysis of calculus, I would say, of computing derivatives, and check that those points must be critical points. Okay, so this is how this is proved. And the actual conjecture of Arnold is not just about this number 2, which is the same as this number 2 here. It's really saying that this number, if you think about it correctly, is related to the number of critical points of a Morse function. Okay, so now I want to explain how, why this conjecture of Arnold about the number of fixed points is not obvious. So first of all, there was some condition which I didn't highlight very much, which is I said symplectic transformation, and I said which is isotopic to the identity, which means you're only looking at transformations so you can deform from the identity to this transformation without ripping the space apart. So there is a theory, very well understood theory, for how to think about things. You can think of them in terms of vector fields. So a vector field on a manifold is at every point I have a tangent direction. Okay, and if I have a tangent direction at every point, I can follow this tangent direction, and I will obtain a map from this manifold to itself. And every diffeomorphism of a manifold, which I can connect back to the identity, can be produced by integrating, as we say, a time-dependent vector field. So now there's a theorem which is much, this was probably, proved somewhere around 1940, and it says if you have a manifold and it satisfies some topological condition, which I will say something about in a second, called that the Euler characteristic vanishes, then you can find a vector field with no zeros, okay, and vice versa. If you can find a vector field with no zeros, then this topological property of the Euler characteristic vanishes. So I need one slide to get back to this, but let me say what it means concretely. So remember, in a few slides ago, I was introducing this torus, this surface that lives in space, the boundary of Schwinsch, and I described it. I said it's very useful to be able to go back and forth. Okay, so now I want to describe it back in this picture using a square. So if I draw the square, at every point I have a little arrow pointing in the 1, direction. So this is a vector field. This is exactly what it means to have a vector field. Okay, every point you have a tangent direction. Great. So what I want to illustrate for you, at least just start giving you some idea, is that you can use this vector field to produce a vector field on the 3-sphere. So 3-sphere is you take the R3 that we live in and you add a point at infinity. It's not the boundary of the globe that we live on. It's some spaces that we cannot visualize from the outside. We can only visualize it from the inside, which is the 1-point compactification of Euclidean space in 3 variables. So we can construct from this a vector field on S3, on the 3-sphere, which is with no zeros. So how do we do it? Well, first thing I'm going to do is something a little bit strange. I'm going to take this central axis, the z-axis, okay, and on it I'm going to have my vector field pointing up. Okay? And if it goes up to infinity, and at infinity, well, infinity up there is the same as infinity down here. So I go up there and I come back. Okay? So that's on this circle actually in S3, vector field is just pointing up. Now, there's another circle which I want to highlight, which is this circle in red here. So this is the circle of, I just picked it, radius 1 in the xy plane. Okay? On that circle, I would like the vector field to go this way. Okay? To just go counterclockwise. This counterclockwise, that's counterclockwise. Okay. So these two things are going to be fixed. And now I will explain to you how to describe the vector field in the rest of the space. And you do it as follows. So you take this circle, the red one, and you imagine now that you have a very small shell around it. Okay, that's shown here. This was supposed to be blue, but it's shown in gray. Take a very small shell around it. And on this shell, now I need to pick a vector field. How am I going to do that? Well, I'm going to take this vector field over here, and I will transport it to this shell by the identification which I tried to show you early on when I explained to you that a torus can be thought of both as living in R3, in Euclidean space, and as being a square with disidentifications. Okay. And when I do that, so this curve is going in this direction, so it's moving both in the horizontal and vertical direction, and if you try to draw what it looks like, it's going to look like this. It's going to wind around once in the meridian and once in the longitude. So this was for a very small shell, but actually this construction can then be extended. If you imagine that you take this very small shell and you make it bigger, bigger, and bigger, you're going to fill the whole space. Okay? So those are vector fields. And the key point that I'm trying to get you to see is that, on the 3-sphere, I just made some assertion that functions must have a min and a max, okay, and therefore must always have a critical point. On the other hand, vector fields don't need to have zeros. Okay? So there's this difference between properties of functions and properties of vector fields. Okay. Okay. Properties of functions and properties of vector fields. Okay. And we need to explain them. And now we take yet another step in abstraction. And the step in abstraction that we need to be able to explain this difference between functions and vector fields is called cohomology theory. So, we talked about manifolds, differential forms, symplectic manifolds. Now we need something completely different. We need to talk about invariants of manifolds. Invariants often take value, numbers are great, like the area, But there are things that are more complicated than numbers, like groups. Okay, so homology or cohomology, I guess, the cohomology of a space is some kind of either abelian group or vector space, depending exactly on how you set it up. Most important thing that I want to say about it is that there's one number for each integer, positive integer, non-negative integer. Okay, so that's denoted Hij(x). I is the integer that you pick, and x is the topological space. Okay? I'm not going to say anything about it, other than the fact there are many ways of constructing it. One way using differential forms, that's exactly what theorem was doing. Another way, has an older history, which is you take the space and you break it up into triangles. It's called triangulation, like a mesh, if you're more of an applied person, or a cubical mesh. And then you construct some invariant out of that. Another way, which is kind of the standard way in algebraic topology textbooks, is you study all maps from triangles or higher dimensional simplices to your target, and you just build by hand some very complicated group out of it. And you take some subquotient, and you call that the homology group. Whatever it is, it's some group, it's some invariant. And all ways of thinking about homology derive from Poincaré's original insight that what you should do if you're studying a manifold is you should look at its submanifolds. Now, this isn't really Poincaré's insight. This is probably like Riemann's insight. Riemann realized that if you think about what we now call Riemann surfaces, the most important invariance is the genus, and the genus can be thought of as the number of circles that are independent. But Poincaré then extended this to higher dimensions, especially in dimension 3 with the Poincaré conjecture and his first failed attempt to prove it. Okay, so now we're going to take whatever we were doing with symplectic manifold and add some kind of groups to it. Okay, there's a marker there. It says 13 out of 14, so only 2 more slides. So the relationship between functions and cohomology theories was first understood by Morse. Okay, so the key point that he realized is that there are 2 ways to extract a number from a collection of groups that are indexed by the integers. Okay, so one of them is you just take the rank of the groups. Okay? So if you have a collection of groups indexed by integers, you call that a graded abelian group. You just take the sum of the ranks. Okay, so if the first one is z and the second one is z, you say add them together, you get the number 2. The other one is you could take the alternating sum. Okay? Everything that is even contributes its rank, and everything that is odd contributes minus its rank. And the Euler characteristic is exactly that. The Euler characteristic is, if you've ever seen this Gauss formula, you take the number, which shows up in graph theory, for example, take the number of faces, you subtract the number of edges, and you add the number of vertices. So to subtract the number of edges is this minus that you introduce for things which are odd. Okay, now it's obvious that the first thing is bigger than the second thing. I mean, even if you take the absolute value. And now what Morse realized is that you can, in fact, extract these groups, which can be computed using all kinds of different methods. Okay? These cohomology groups, you can extract them by studying critical points of Morse functions. So just this base, if you take of generic function, if you take a smooth function, you look at all the points where the derivative is equal to 0, and then you need one more piece of information. You need the space of gradient trajectories. So what are the gradient trajectories? They are solutions to ODEs. So imagine that my function that I drew over here, so this is some kind of height function. Okay? Like I'm on some mountain, okay? Walking in the mountains, and this is the highest point in the mountain, and this is what's called a saddle point. It's a point where there's a direction where you can go down and a direction where you can go up. And the gradient trajectory will be, if I go at the point over here, I can ask myself, what is the fastest direction in which what is the direction in which I can go the fastest, if I can descend the fastest? Or another way to say this, if I were to take a ball and I drop it at the top and I punch it, move it a tiny little bit, it will roll down the hill. The path that it will follow will be the gradient trajectory. So what Morse realized is that if you keep track of these critical points, there's 2 over here. And if you look at the gradient trajectories between them, more importantly, there will be some situations where there's like 1 parameter families of gradient trajectories, and then they will converge to other ones. So if you study the space of all gradient trajectories, from this information, you can extract the homology of a manifold. And that essentially immediately tells you something about the minimal number of critical points of a function. It tells you that if you can compute the homology group, you can extract the minimal number of critical points. Okay, and now finally come to the thing that was supposed to be the last thing in the lecture, which is what Floer theory is about. So what Floer had some insight around 1989, so a long time ago already, that says that this idea of having critical points and gradient flow lines between them, you can apply it to questions of symplectic dynamics as well. You can apply it to understand this question that Arnold asked about transformations. Maps would preserve the symplectic form, which is isotopic to the identity. And I'm not going to give a precise statement except to say that one way he proved it, one consequence of that he proved is that you can extract the cohomology of a manifold from that's not supposed to be critical point, supposed to be fixed point of a symplectic diffeomorphism, and from the gradient flow lines of what is now called a symplectic action functional. So this is not a precise definition. The reason it's not precise is because the gradient flow equation that you have to study is not something that I can just show you, like you have a ball and it rolls or something like that. It's not something, it doesn't take place in finite dimension, it takes place in infinite dimension. And really the thing that Floer did is he translated it to a PDE, okay, to a partial differential equation. This partial differential equation has a source, which is some kind of Riemann surface. And the easiest way to think about it is I'm going to take the cylinder. Okay. But the subject is not really about studying these cylinders, because Floer discovered, in fact, a little bit some work before then, that there's some kind of limit points of these spaces of solutions, which are not just two solutions, but rather have some kind of what's called sphere bubblings. More complicated Riemann surfaces appear. So this is the last thing I want to say, which is that the subject of symplectic topology, in which I've been working for maybe almost 20 years now. So in some sense, what we are doing is we are trying to answer these questions, these dynamical questions, from many of which were from a long time ago. Also, some other questions from topology, which I can tell people about later if they're interested in. But the key tool that we use are these kind of solutions to PDEs, which are generalizations of the kind of ODEs that you see when you study gradient flow equations, and the algebraic structures that you can extract from them. So there's these black box theorems, which I didn't give you details about, which basically say you can do algebra, okay? You can extract homology, whatever that is, which is the graded abelian groups, out of studying these PDEs. And that's the central thrust of the subject at the moment. Okay, so I think I will stop here. Thank you.
So thank you for your insightful presentation. Now we're going to pass to questions. If anyone has a question, please raise your hands.
I just want to ask, I've seen the name action functional in physics a lot. I don't know if it's the same thing or not. Because we usually use the same name for something very similar.
So yes. The action functional in physics shows up in many places. So some places it shows up is in like optics. And in optics, it's actually not analogous to this one. It's more like the action, it's in pure mathematics, it's closer to the functional that appears when you study geodesics. It's the shortest path between things, okay? So there is actually an action functional that is very similar to this one. It appears in quantum field theory, okay? So in some sense, in quantum field theory, there are some functionals where people want to minimize or perform some integration over something which is infinite dimensional and it doesn't make sense, and mathematicians have been spending many, many years trying to make sense out of it. It is not this one either, but it is analogous to it in the sense that it has the same feature where you are doing some construction on an infinite dimensional space and the standard mathematical tools do not seem to work. Let me just say that. You have to invent new ones. But again, they're not so new anymore. Floer did this work in 1987, 88, but it's still somehow quite mysterious.
Is it related to the question of
Hamiltonian versus Lagrangian in this question?
Okay. So the short answer is I do not know how to translate the standard question in physics about whether some system has a Lagrangian describing it, okay, in precise topological language. What I can say is that there is an analogous situation in different symplectic topology, where you can make a similar question. I didn't talk about it here, but let me just say there is a class of symplectic of submanifolds, of symplectic manifolds, which Arnold called Lagrangians, for the specific reason that when you try to, that you can often take a Hamiltonian system in the sense that I described and write it in terms of these submanifolds, right? How they generate very specific Hamiltonian systems. And these conjectures that, I mean, I've been discussing something about Hamiltonian transformations. They're analogous conjectures about Lagrangian submanifolds and their properties. So every statement that I'm making about symplectic, about symplectic transformations, you can formulate a version of it which is about Lagrangian submanifolds. And usually it's much harder to prove in that case.
Bonsoir, et il n'y a pas de souci de poser la question en français. Ouais. D'abord, merci pour cette majeure présentation, déjà qui donne un peu de chemin pour comprendre les vraies notions qui cachent derrière la topologie algébrique. Ma question, en fait, c'est comment la géométrie algébrique est séparée en quelque fois de la géométrie analytique.
Okay, so can I translate the question, make sure I understood? So you asked about algebraic geometry and the relationship between algebraic geometry and analytic geometry. Okay. So analytic geometry, I don't have to figure out exactly what you mean by that, because so when I think a question like this, I think about complex variables. So in complex variables, I can make sense of complex polynomials, and complex zero locus of complex polynomials will be the subject that is studied by algebraic geometry. And analogously, I can study things which I would call complex analytic manifolds, which are things which actually are like manifolds that I described, except that they're the change of variables, instead of being just smooth maps, are analytic maps, maybe complex analytic maps. Okay, so in fact, there is some interesting analogy between what's happening there in symplectic topology, because there as well, there are very delicate questions of flexibility. So algebraic geometry is very rigid. You have polynomials. If you take a polynomial, you cannot, the simplest way to say this, you take a polynomial, if you know the values at, in a small open set in the analytic topology, then you know the values everywhere because there's some continuation property. Now, in principle, complex analysis also has unique continuation. That's a basic fact of complex analysis. Nonetheless, one is able to do much more delicate constructions in complex analysis than in much more flexible constructions. So, for example, you can ask questions of the form, what is the topology of a complex surface, of a complex surface? Okay? Surface means real 4-dimension, complex 2-dimension. And there it's known since the 1950s that the answer is different in the complex analytic setting and the algebraic setting. So that's another version of this rigidity versus flexibility dichotomy.
My question is there a relation between how
one can make some sense out of it. So there is some, I assume the question is coming from some kind of physics way of thinking. Okay. So there is some mathematical way of thinking about the invariants in the world of differential topology that are related to gauge theoretic invariants. They come in many flavors. The simplest one of them is as follows. So very often the way that you formulate you try to formulate gauge theory mathematically is not just about a manifold. It is a manifold with some additional structure on it, and that additional structure we would call a vector bundle. Okay, so you have some vector bundle on the manifold, and the basic idea is the vector bundle is where the fields live. Okay, so now there's a theory developed by Chern-Weil in the 50s and 60s, and then discovered by physicists and so on, which tells you that you can produce some invariance of this situation by performing some integrals. Okay? It's great, it's wonderful. But I'm very bad at integrals. And in fact, there's a completely different way of producing them, which is that you just take these vector bundles and think about somehow maps between them and try to produce, to like count the number of something like you count the number of zeros of a section, of a generic section. You basically like perturb, you have this vector bundle, you perturb, you take a section, you perturb it, and you see where something vanishes, and you just count it. And that produces a topological invariant, which is much more obviously a discrete number. So it's a little bit like this Cauchy. I would say it's all about this Cauchy integral formula. There's always some way of doing it by an integral and some way of realizing that actually it just must be an integer because it's just counting some discrete thing, how many times you wind around. And that kind of, those two perspectives, you can push them into gauge theory and they make sense there as well.
Any other questions? First, I guess I'm not familiar with a lot of concepts that you mentioned here, but I have a question that is a bit out of context, but I'm curious about it. My question is there a theory of like that explains classical or Euclidean geometry? In other words, what is, for example, a square or a triangle, like mathematically, like besides the definition of what we see, or like on a board or something, and besides the other definition of like the analytic definition, which is like a circle is a set of points that verifies certain properties. Like, is there a definition of geometrical shapes mathematically? That's my question.
Okay, so this is a very difficult question to answer. It's not my domain of expertise. So what I can say, two things. So first, there is some subject called synthetic differential geometry or synthetic geometry, which is some attempt at pushing, I would say some attempt at pushing Euclid's axiomatization beyond basic things like what shows up in basic Euclidean geometry. So that's one answer I can give. There is a different answer I can give, which is of the form, it's not going to be something that's going to cover all of Euclidean geometry, but there are many questions of Euclidean geometry of the point. Well, the first thing one proves in Euclidean geometry is you take 2 points, there's one line through them, okay? But then there are many things of this nature, like, you take, whatever, I'm not very good at this, but you take some number of points and you ask yourself, like, how many conics pass through it, or something like that, I think four con. Anyway, so these questions, there is, a thriving and very rich subject in modern mathematics called enumerative algebraic geometry, which studies this. And it studies this in higher dimensions, as well as in dimension 1, but less interesting in lower dimensions. And it has very interesting connections to all kinds of subjects, including representation theory or actually, in fact, symplectic topology. So I'm not sure I can give a better answer than that, other than to point out that there are modern areas of mathematics which might satisfy your question, but I'm not sure either of them will be fully what you were asking for. Okay, again,
Okay, I just have a simple question. You said, I mean, this is the point that really interests me as a physicist, I think. But the thing is, you talk about how symplectic geometry is related to classical mechanics and Lagrange and so on, but I still can't see how this is the case. I mean, just from the, can you maybe flesh out the analogy or just how it's related?
Yes, yes, I can do. It'll take a second. So if you have ever seen a Hamiltonian description of classical mechanics, in the Hamiltonian description of classical mechanics, what is done is one introduces two types of variables. One variable is called the position variable, usually denoted Q, at least in American textbooks, and the other variable is the momentum variable, it's called P. And the thing that these two sets of variables satisfy is that there's some pairing between them. And you use this pairing to start with the Hamiltonian function of P and Q. Like if you have the simplest situation, it's just only some particle moving, it's like norm P squared, something like that. Okay, and then you differentiate it and you do something. What is it that you do? You do some transformation, you put in some signs, you switch some P's to some Q's. Okay, so what is happening from the point of view of symplectic topology is that the space, I don't have my computer, otherwise I would be writing. So you imagine that these P's and Q's, they form some manifold, okay? So it's called the phase space, okay? It has 2 times as many variables as the space that you live in. So for example, if we're doing something about R3 and we just have one particle moving, this particle has a position, that's 3 variables, but also a vector, a momentum vector, that's another 3 variables, so 6-dimensional space. On this 6-dimensional space, there is a symplectic form. And the symplectic form, I didn't write it, it's a 2 form, it's supposed to pair 2 things together, it pairs Pi with Qi, okay? And using this, you obtain some formalism for taking any function and producing a flow, and that is the Hamiltonian flow that you produce. Now, the advantage is you can then formulate this without actually writing any equations. Okay? You can do this in a situation where very easily do this in a situation where Q satisfies some constraint. It's not actually, particle is not moving in space freely, it's constrained to live on some surface. And now suddenly you're able to do things in much more generality, but again, it depends on what question you want. If you're asked some specific question whose answer is something where you need like 12 decimal places, these methods are not actually going to help you that much. If you're asking some question of the form, which is what Poincaré was asking, should I expect that the solar system is stable? Okay? Is there some theoretical reason why, I don't know at the time how many planets they had, let's say 9 planets, okay, going around the solar system would have the property that you could find a stable point of this flow. Okay? So that is what, without actually doing a bunch of numerics, because he understood very early on you cannot do the numerics. That's what this machinery is for.
First, thank you. I really appreciate how you explain the concepts. And in your presentation, you said the Morse theory. And I want to know what is the analogy between Morse theory in infinite dimensional and the Floer theory in infinite dimensional in the loop spaces.
So it's a little bit confusing because what happened is that Morse, so I know this because I've been reading the papers recently. So Morse wrote 2 papers, one in 1924 and then one in 1925. And the paper in 1924 was about Morse theory in finite dimensions. It had didn't have pictures actually, but if it had pictures, it would have had pictures like this. Okay, and in the subsequent paper, 1 year later, he was discussing Morse theory in infinite dimensions. But what kind of Morse theory was he doing? He was doing this this thing that I was saying about understanding paths which minimize length. It's called geodesics. So if you're basically looking at straight lines, but on spaces which are curved, and he proved something which is extremely interesting. Let me go back to this picture. Great. So if I look at this blue thing on the right, it's very easy for me to just explicitly parameterize all the paths which minimize the length. Okay, everything is explicit. Look at this picture on the left. How could you possibly figure out what all the paths are that minimize length? I mean, somehow by the time you sit down and write the actual differential equation that you would need to solve, it would have way too many terms that for you to be able to control. So Morse proved that, in fact, in some appropriate sense, homological sense, there are exactly as many geodesics on the left as there are on the right. Okay? And the way he did this is by studying something also called the action functional, okay, on the loop space. But for reasons that are a bit hard to explain, there's some technical reasons, his action functional can always be reduced to a finite dimensional question. Even though you're looking at maps from manifolds to other manifolds, so this is some kind of infinite dimensional, in principle, infinite dimensional Fauché space, the nature of the question you are asking is such that you can reduce it to finite dimension. Okay? So that made it possible for him to have proved this result in, again, 1925, which is, 100 years ago. The questions that appear in symplectic topology about Hamiltonian dynamics appear at first to be similar. But it took about 50 years, more than 50 years, to make any progress on them, because it turns out that they do not have this finite dimensional reduction, that you have to do something genuinely infinite dimensional to answer them. Maybe that's all I will say.
Professor, you ask the question if the geometric objects like skeleton. Skeleton is how you can describe this skeleton in a topological space like this. The problem is in gaming. The human or the agent in but let's say in artery. I can't generate in artery, but I can generate in a metric space. By the contrast, is rigid objects. You can the distance between two algorithms, the distance between and algorithms and each vertex is mapped to location in this metric space. And we compute the distance between the two is fixed. How can this object skeleton is generalized in a topological space? No, don't use the distance. No, use and the problem is if we know the trajectory in some node, and we need to predict the trajectory in lot of and other node, and the project and this object is rigid. So this is a problem.
Okay, I'm not sure I can answer the question. I think maybe after the lecture, if you can explain to me more precisely what you want, we can discuss it. But somehow, I'm not able to parse enough of what you said, also especially not to relate it to what I said. So let's do that after.
So it says here that a basic result in the subject is that the total surface area is an invariant of symplectic surfaces. You said, I believe, that this was as long as the number of holes was the same?
Yeah, that's what I said. And the underlying differentiable manifold.
Yep, exactly. My question is about the definition of holes from a topological point of view, since we have this idea in popular culture that the topologist does not make the difference between a mug and a donut. And I just want to know what a hole truly is, topologically speaking, especially since in higher dimensions it might not be as obvious as in 2 dimensions.
So the definition in higher dimensions is exactly what this homology theory is about. That is the easiest way of measuring it. You know, I mean, in this dimension, I mean, you can just use Poincaré's definition. And Poincaré's definition was something along the lines of, what is the maximal number of circles that you can put on your surface so that you cannot deform, you know, any one of them to a collection of the other ones? union of the other ones. Now, technically, you have to be careful because you have to put some weights, maybe something like that. But basically, here, there are, there's circles that go one way and circles that go the other way. And, the genus of this, you divide this number by 2, and the genus of the surface is 1. If you take a 2-sphere, you can take any circle you want, and you can just shrink it to a point. So that's, now, you start with this intuition, and then, indeed, it's a good question. How do you generalize it to higher dimensions? And I don't have a very good answer to that, other than to say, that's what homology theory is, or rather, more precisely, it's probably not what homology theory. Homology theory is the most convenient way of extending this intuition in this dimension to higher dimensions. That's really what it is.
So thank you everyone for all your interesting questions, and thank you again, Dr. Mohammed, for this interesting and very insightful conference.
احنا في اللي عطلنا ورا هذاك مشكل ما عرفناش علاش اصلا